Today we will discuss laser interaction with plasmas embedded with clusters. We will discuss, after making some introductory remarks, the process of ion Coulomb explosion of clusters, whereby we produce neutrons, and then I will discuss surface enhanced Raman scattering, and then Rayleigh scattering, and laser interaction with carbon nanotubes, and then I will make some concluding remarks. The references for today's presentation are: there is a classic paper by Dittmeyer, who was the first person to demonstrate ion Coulomb explosion of clusters and production of neutrons, in his landmark paper in 1996. Then we did some theoretical work on this with Professor Liu and myself, and this is published in Physics of Plasmas in 2000. And I would also like to refer to a very classic paper on surface enhanced Raman scattering by Moskowitz, published in Reviews of Modern Physics in 1985. Well, let me mention two experiments that motivated a lot of interest. One was conducted more than 2 decades ago. What was done was that there was a chamber in which some gas was filled, and these gas molecules were spread all over, and some experiments were conducted by shining laser light on the gas to observe Raman spectrum. So people were wanted to see Raman scattered light, incident light, and this Raman scattered light they wanted to see. But the signal was very feeble, very, very feeble. Accidentally, they found that if the light is somehow directed towards a silver plate with a rough surface, so there are some roughness over the surface, and when the laser light was incident on this, then the Raman scattered signal got amplified or enhanced by 1,000,000 times. This was a very spectacular observation, that what happened, what does the roughness of the silver surface do to enhance the Raman scattering process by 1,000,000 times. The Raman spectrum was the characteristic not of silver, it was the characteristic of the molecules of the gas that was filled in the chamber. So people believed that there is gas roughness is equivalent to some sort of particles over which these gas molecules were adsorbed, and Raman scattering was taking place from these adsorbed molecules on these some sorts of roughness, means like clusters. So this was one observation that motivated a lot of interest. And second experiment was conducted a decade later, or more than a decade later, by Dittmeyer, and that experiment was like this: that if you take a chamber, or rather a vessel containing a high pressure gas, and have a nozzle here, very small thin nozzle here, then when the gas gets out, it forms a plume, sort of a plume here, this sort of a plume. He irradiated the gas by means of a laser of this sort. This was the intensity distribution of the laser. Laser was traveling in this direction. What was observed, that when the gas was filled in this chamber, deuterium gas was filled. When the deuterium gas was filled at room temperature and at high pressure, then roughly 95% of laser energy got transmitted, and no spectacular observation was made. However, when the temperature of this was lowered to liquid nitrogen temperature, and then this was found that nearly 95% of laser light was absorbed, only 5% was transmitted. So this was when room temperature or high temperature, and at a low temperature the same experiment demonstrated. If you have a nozzle here, plume was like this, laser light was coming like this, and only 5% transmission was there. Besides the laser which was transmitted, they found a huge flux of neutrons produced. So, these two observations I consider this to be groundbreaking observations. One was the enhancement in Raman scattering by a million times by the roughness on the silver surface, and second was the generation of neutrons and very strong absorption of laser by a gas jet or gas jet plume if the gas was kept at a low temperature. What was then detected was that this gas was qualitatively different than the gas jet here, and the difference was that this contained clusters. And this is the presence of clusters that made this experiment qualitatively different than this experiment, and the size of the clusters was typically about 50 angstrom radius. So, now I would like to examine what physical effect a cluster would do on the laser coupling with a plasma. Well, in this case, laser when travels through a gas, whether with clusters or without clusters, it ionizes the gas if the intensity is large enough. And the process of ionization is called tunnel ionization. Let me enumerate the processes. The first process is the tunnel ionization of the gas. This occurs when, because in a gas you are having nuclei, atoms with the nucleus in the middle and electron going around this. This nucleus, this electron. So, electron always feels a Coulomb force due to the nucleus. Whenever the Coulomb field, which is equal to E upon, if charge of the nucleus is plus E, this electron is minus E, then E upon 4 pi epsilon 0, the distance from here to here, suppose A, then A square, this is called Coulomb field. So, when an electron revolves around the nucleus at a radius A, it experiences an electric field of this order due to the nucleus. And if you can have a laser with laser field strength greater than or of the order of EC, then this electron can be released instantaneously out of this atom and the atom get ionized, and this process is called tunnel ionization. Keldysh wrote a pioneering paper on this, and that explains the process with clarity. Now, this condition is satisfied typically at intensities of the order of 10 to the 14 watt per centimeter square. So, whenever the laser intensity exceeds this number, then laser can cause instantaneously or very rapid ionization via tunneling. And if you are having a system with clusters in which there are many atoms, so if I have a cluster of radius RC, suppose RC is the radius of the cluster, when the laser shines on this cluster, this is my laser coming in here, but this is my direction of electric field, and as if the intensity of laser is chosen higher than 10 to 14 watt per centimeter square, then this laser can also cause tunnel ionization of all the atoms inside the cluster and converts it into a plasma ball. So, deuterium ions are left by themselves as ions, but they are in the ocean of free electrons of same density. So, you are having two overlapping spheres, a ionosphere and a electronosphere, but the electrons do not belong to a particular atom, they belong to the entire sphere or cluster. Now, let us consider what will happen when the laser sees a fully ionized plasma ball. I think in order to understand the physics of this process, well, physically what would happen is like this, that when the electron and ionosphere, they see the electric field of the laser. Laser is coming like this is the electric field. Ions are very heavy, they will not respond to the electric force due to the laser, but the electron cloud will oscillate and will move. It may move something like this, it may move away from here, it can get shifted. So, what will happen? That there is a overlapping region where the ions and electrons both exist in this region, but there are some regions, some electrons are additionally electrons are moved out and some electrons are in deficiency here. So, this is a distorted overlap where large part of the two spheres are overlapping, and we will show quickly that the electric field produced by the charge separation, when the electrons center of electron charge is somewhere here and ion space charge center is here and they are shifted by a distance delta, then there is an electric field produced in this region and that pulls back the electrons. So, the basic thing is that in a sphere, a spherical ball, when the electrons are displaced, they experience a restoration force, and that is the key to understand the two processes that I just mentioned. Now, in order to drive an expression for the electric field in the overlap region, let me consider step by step. So, consider a ionosphere first. I will consider an ionosphere of density n0 ions per centimeter cube. So, charge density is n0 e, where e is the electronic charge magnitude. So, this is the charge per unit volume of the sphere. Forget the electron sphere for a moment. This is the center of this sphere, and I want to find out the electric field at a distance r from the center of the sphere. So, what I do? I use the Gauss divergence theorem, which says that E dot ds into epsilon 0, this is called total outward normal flux. Epsilon 0 into E, epsilon 0 is the free space permittivity, epsilon 0 E is the displacement vector, dot ds is the total flux linked with a closed surface, is equal to charge enclosed inside the surface. So, now consider a Gaussian surface of radius r. R is the distance at which I want to find the electric field due to this charged sphere. So, I consider a spherical Gaussian surface and calculate this quantity. By symmetry, the electric field is in the radial direction. So, this is ER and total surface area would be 4 pi r square. So, this becomes epsilon 0 ER 4 pi r square is equal to charge enclosed would be volume of the sphere, which is 4 pi by 3 into r cube into n0 e. So, when the point of observation lies inside the sphere, then the charge enclosed is given by this, and what you get here is ER is equal to n0 e upon 3 epsilon 0, and I will denote this by the vector sign in the radial direction. So, this is the electric field seen at a distance r from the center of a sphere. This is due to a single sphere, ionosphere. But when we have a displaced electron sphere also, the center of the electron sphere is suppose at a distance delta. I have moved this by a distance delta, this is the ionosphere center. So, the electron sphere suppose I have shifted by distance delta. Then what will happen? The electric field at the position of observation at r due to the electron sphere centered at delta distance away from the ion center displaced with respect to ion center, then how much this would be? I will call this as E dash. That would be equal to, charge is negative, so minus n0 E by 3 epsilon 0, and the position of the point of observation from the center of the sphere would be ion minus delta. So, the ion field I got earlier, electron field I got now, add the two fields in the overlap region. So, the net field in the overlap region would be E is equal to n0 E upon 3 epsilon 0 delta, which is a constant. So, let me draw a picture. I have a ionosphere, then I have a displaced electron sphere. The center of the electron charge is here, the center of the positive charge is here, the distance here is delta. So, we find that the electric field is in the direction of electron displacement, is in this direction, and it is uniform. Now, what is the force on the electron? Electric field, if you multiply by the charge of the electron, then the electron will experience a force. Every electron will experience a force. So, each electron experiences a force, a restoration force, is equal to minus EE. So, multiply this quantity by minus E, and this turns out to be equal to omega p square by 3 delta, because I am defining omega p, the plasma frequency as before, n0 E square upon m epsilon 0. So, multiply m also here, delta into m, this to the power half. So, there is a restoration force experienced by every electron. Now, let me write down the equation of motion for an electron inside the electron sphere in the presence of the laser field. So, I want to examine the response of the cluster to a laser field like this. So, let me take laser field like this. Suppose this is polarized in the x direction, this is my x direction, this may be z direction. Amplitude of the laser is suppose A, exponential minus I, omega t minus kz. This is the field of the laser. But the distance z is very tiny when you go from one end of the cluster to another end, and hence this term is not really significant. So, in order to find the electron response, we solve the equation of motion for the electrons inside this electron sphere, and every electron is displaced by a distance delta. So, delta I will call is the electron excursion. Which will be in the x direction anyway, and the equation would be m into d2 delta by dt square is equal to the laser force, which is minus EEL, and plus the restoration force, which is minus m omega p square by 3 into delta. This equation can be solved easily because electric field goes in time as exponential minus I omega t. So, in the quasi steady state, delta should also behave in the same manner with time, and you can take delta to vary as exponential of minus I omega t minus kz also. So, replace d dt by minus I omega, and that gives me delta. The displacement or excursion of the electron from the nucleus of the ion, or rather electronosphere with respect to the ionosphere, is equal to EEL upon m omega square minus omega p square by 3. This is a beauty here, that this quantity, this expression has a resonance in the denominator. At omega equal to omega p by root 3, the excursion would be very large. So, if you choose a cluster whose plasma frequency was such that omega p is equal to root 3 omega, where omega is the frequency of the laser, then the electron cloud will oscillate with a very large amplitude. This is a very important thing. Now, if I calculate the electric field due to the space charge in the overlap region, let me, using this value of delta, how much is this? Let us see. Please, that will be a very revealing thing. The space charge field that I just calculated in the overlap region, where the two spheres overlap, E is equal to, it was, let me just write down, n0 E upon 3 epsilon 0 into delta, and put the value of delta that I just evaluated. It turns out to be n0 E square upon 3 m epsilon 0 multiplied by omega square minus omega p square by 3 into electric field of the laser. So, if you compare the amplitude of the electric field of the space charge that has been induced by the laser field, this turns out to be much bigger than this, in the neighborhood of this resonance. So, E upon EL is equal to, this quantity is omega p square by 3 divided by omega square minus omega p square by 3, and this goes to infinity as omega approaches omega p upon root 3. This frequency omega p by root 3 is called plasmon resonance frequency. So, laser field, if it can do any effect on charged particles, then inside a cluster the effective field that has been induced by this laser is resonantly enhanced by this factor. And this is primarily the basis for surface enhanced Raman scattering by million times, and we shall discuss that. This is primarily the physics. There is a resonance that arises due to space charge oscillations of the electron oscillation with respect to ionosphere, that gives rise to this resonance, and this resonant field enhancement manifests itself in the form of surface enhanced Raman scattering. We shall discuss that. But before I go to discuss the surface enhanced Raman scattering, let us see what will happen to the cluster. When the laser intensity is significantly large, your electron cloud is really moving out, and back and forth. And if you choose very large intensity of the laser, then the electron cloud can completely move out of this. So, for a very significant part of the laser period, the ionosphere is rendered unneutralized because electrons are not there, so it becomes a positively charged sphere, and this will undergo what we call as the Coulomb explosion. Well, if the intensities are in the intermediate range, that the electron cloud is partly overlapping with the ionosphere, moving out significantly but not completely. In that case, one should develop a model where the electrons and electrons neutralize partially the space charge of ions but not completely. Anyway, let me first consider the case where ideally if I remove the electrons of the sphere, how the ions will respond. You know, it has been a classic problem in fusion research that if you want to produce thermonuclear fusion in lab, then you need to supply energy of the laser to the ions, and ions are very heavy. So, whenever you have a plasma, the electrons oscillate more vigorously than the ions, and energy is taken by the electrons, and ion energy is very tiny. So, people have always been worrying that could be the efficient way to transfer energy from laser to the ions, which are heavier than electrons by several orders of magnitude mass. Now, let us consider a ionosphere. So, I am now talking about the ion Coulomb explosion. Consider a ionosphere, forget the electrons for a moment. This is the center of the ionosphere. Ions have to repel each other, and I want to estimate how much energy they will gain. The radius of the ionosphere is RC, initial radius of the ionosphere. Now, consider an ion placed at a distance Ri from the center of the ionosphere. I want to find out how much electric field this ion will experience, how much the force this electron will experience. Now, just I calculated that if this is a fully ionized sphere of charge density N0E, then the electric field at position Ri, which will be in the radial direction, this is equal to, I just calculated, and this was equal to N0E upon 3 epsilon 0 into Ri. This is the electric field that will be produced. Well, this is the radial direction, so I do not really have to write this. Well, otherwise put a vector sign here, forget this R here. So, the electric field produced by the space charge of this ionosphere at position Ri is so much. When this sphere expands, one thing you may note that every ion, this ion will experience a force which is proportional to this electric field charge, this field times the charge. Now, the ions which are at a larger value of Ri, they will experience a bigger force. So, when this sphere expands, then the ions which are farther from the center, they will move faster, and the ones which are closer to the center, they will move slowly. As a result, there will be no crossing of ions. So, when this has expanded to a bigger size of this form, suppose this is the bigger size it has acquired later on, then the ion which was here, it has moved to somewhere here, then the charge which was contained in this radius Ri has moved to a distance r, but the total charge contained will be same, because the charge that was contained in this inner sphere, the same sphere has expanded. So, the charge which was here in this radius has moved to a bigger sphere of radius r, but the total charge remains the same. So, if I calculate the electric field seen by this test ion that originated at Ri, when it has moved to distance r, the electric field by the same ion at position r would be the total charge in this sphere, which will be 4 pi by 3 into N0E Ri cube. This is the total charge upon 4 pi epsilon 0 into r square, and that is in the radial direction. So, this is the electric field seen by the same ion. Means as this sphere undergoes Coulomb explosion, the ion which was starting at position Ri with 0 velocity, as it moves out, it sees a decreasing electric field, because the distance as r increases, field will decrease. So if you calculate the work done or energy gained by the ion as it goes from Ri to R, the energy gained by the ion originally at Ri on reaching distance r, this energy would be Ei is equal to the electric force on the ion, which is E times E r multiplied by the distance travelled. So dr, if I multiply and integrate from initial position Ri to position r, this is the work done. If you evaluate this quantity, it turns out to be E is here, E is there, so this becomes N0 E square upon 3 epsilon 0 Ri cube, and this turns out to be equal to 1 upon Ri minus 1 upon R. This is the energy gained by the ion. If I choose Ri, obviously it has to be less than Rc, because the total cluster radius is Rc. So ions are there between 0 and Rc, and this R could be maybe when the cluster has expanded to a radius of 2 Rc or something. So this could be smaller than this, and hence the typical energy gain will be of this order: N0 E square Ri square upon 3 epsilon 0. Means the ions that leave from higher value of at higher distance from the center of the ionosphere, they will gain more energy. Their number will also be more. So Ei, the energy gain, is a function of distance from the center of the sphere. And if I want to calculate the energy distribution, I will do something like this. Consider the ionosphere. I am considering an ion which is somewhere at Ri, and another group of ions which are lying between Ri and Ri plus Dri. So this is my Ri distance, and this distance between the two concentric spheres is Dri. So the ions originating between Ri and Dri will have energy in the range Ei and Ei plus Dei. What I am saying here is, what is the number of ions contained in between these two concentric spheres? Let their number be Dn. That would be the total volume of this region, which is 4 pi Ri square Dri. This is the volume, and the number of ions per unit volume is N0. So charge contained in this would be this into E. Sorry, not charge, I want the number of ions only. So the total number of ions contained in this region will be so much, but Ri and Ei are connected. I just wrote down that relation, that energy of the ion is equal to N0 E square by 3 epsilon 0 Ri square. So, Ri I can write down in terms of Ei, and Dri I can write down in terms of Dei. I can differentiate this. Dei is equal to N0 E square upon 3 epsilon 0 2 Ri Dri. So, Dri is related to Dei. You can connect this. And what is funny, that this turns out to be some function of Ei into Dei. This coefficient, because Ri I can write in terms of Ei, Dri I can write in terms of Dei. So, I can write down this entire coefficient here in terms of Ei. This is called the distribution function. So, this is the energy distribution function of ions, and this turns out to be proportional to Ei to the power half. So, the interesting part is that the distribution function turns out to be Ei to the power half. One can easily calculate this number. And this quantity, if I plot here, then distribution function of ions that are produced from a single cluster, if it is 100% electron evacuated as a function of Ei, this goes like this. This is the distribution function. Now, consider the illumination of a clustered gas by a Gaussian laser beam. Suppose I choose a laser beam of this sort and shine this on a plume like this. Then this is the region where laser is falling. So, whatever clusters are there, those clusters will see the laser field. However, the clusters at the center of the laser or laser axis is the laser axis. They will be experiencing a stronger electric field of the laser, and hence they will undergo a stronger excursion, delta will be large, whereas the clusters which are encountered on the periphery, they will see a smaller laser field, and hence the electron evacuation will be less. So, one should improve the model to take into account the intensity variation of the laser as a function of transverse distance, and when you take that into consideration, the clusters on the laser axis will be fewer in number, but as you move radially away, the number of clusters available at the shoulders will be larger and larger. So, it turns out that the distribution function, if you calculate like this, Fi turns out to be a decreasing function of Z, of Ei. For details, I would simply refer the readers or the audience to refer to our paper in which we have done this calculation. I have already given the reference in the beginning. But the interesting part is that this energy could be typically of the order of 10 keV for clusters of radius of the order of 50 to 100 angstrom, and laser intensity is like 10 to 15 watt per centimeter square. That is the advantage, that the intensities that are used in laser driven fusion to produce neutrons are 3 orders of magnitude larger intensities, but here the intensities are 3 orders of magnitude less, and the protons that you are producing are around 10 keV energy. Now, let us see what is the consequence of this. These deuterium ions from clusters collide with each other. So, if there are many clusters, one cluster is here, another cluster is here, they are expanding like this, these are expanding like this, another cluster is here, they are expanding like this. So, they will collide, these deuterium ions will undergo fusion, and the reaction is deuterium, 1d2 plus deuterium 1d2, this is the atomic number, atomic weight. It undergoes fusion producing 2He3 helium plus neutron and releasing about 2.5 MeV energy. So, the energy required for this fusion reaction is 1020 keV, but the energy produced is in MeV, and this is how the neutrons are produced. So, the Dittmeyer experiment was a demonstration of this reaction taking place, and this is a tabletop laser that can do this job. So, this appears to be a very efficient, cheap source of neutron production, and this can be used for several applications. So, this was one thing that I wanted to mention to you. And second thing is surface enhanced Raman scattering. Let us see what is this, how does it manifest in surface enhanced Raman scattering. What happens is, if I take a silver plate and suppose there is some roughness, you can model the roughness like some silver particles of various shapes. I made the calculation for movement of electrons in a spherical particle. People can make, or people modeled the motion of electrons in a non-spherical particle. But I will, for the sake of physics, I will forget the shape. I will consider the particles that are placed or roughness as particles on the surface, and suppose the laser is falling in here. And there are some molecules of air adsorbed on the surface here. These are the molecules adsorbed on the surface. I am showing them separately, but they are essentially attached to them. So, these blue dots are essentially the molecules of air adsorbed there. When laser light falls on a dust particle, on a particle which is also a silver particle, in that case this field is enhanced by a factor. So, E inside the particle is equal to the laser field that has come out from there multiplied with the enhancement factor, which was omega p square by 3 upon omega square minus omega p square by 3. What has been seen that if these particles are not spherical, they are spheroidal, then this 3 is multiplied by a quantity called beta, and this beta depends on the shape. So, for certain particles beta is like unity, for others it could be more than 1, and this resonance condition can be certainly satisfied for some of the particles. So, when you are shining visible light, laser light on this rough surface of silver, this is silver, then these particles will see an enhancement of field by this factor. Beta is a typical shape factor that depends on the shape of the particle. So, now the molecules that are sitting on top of these particles, they will not see the laser field because that is too feeble, but they will see the field due to the space charge, this E field, which is orders of magnitude bigger. So, the scattered field will be enhanced by this factor. Now, how the Raman scattering takes place, let us understand this problem. In Raman scattering, consider for instance chlorine molecule. Chlorine molecule will have 2 chlorine atoms which are vibrating with respect to each other. When laser light comes in, these oscillating molecules also experience a oscillating electric field of the laser. Suppose they are oscillating with vibrational frequency omega b, the laser frequency is omega L or omega, simple omega. So, what happens that the nonlinear current that is induced here has a frequency omega plus omega b and omega minus omega b. So, the laser field on when impinged on vibrating molecule of chlorine for instance, it will induce a current on the system which will go as at frequency exponential of omega plus minus omega b I times into t, and this gives rise to the field. Now, what is happening that these oscillatory dipoles, oscillatory atoms or molecules adsorbed on these particles, they induce a field. If they were in free space, they will induce a small electric field, but that induced field is also enhanced by the particles here, because particles are there. So what is happening? It is a two-way enhancement, that the incident laser field as seen by the electrons of the cluster or the particle is enhanced by this factor, and in this presence of this field, when the molecules oscillate, the oscillatory motion produces some equivalent current, and that induces a field which is enhanced further by the similar factor. It is a double enhancement of the field. So, a scattered field is enhanced by the square of this factor, and hence the intensity is enhanced by a square of the field. So, it is a 4th order of magnitude, 4 to the power 4 enhancement, and that becomes very huge. So, the Raman scattered signal E scattered goes as, this is induced current which goes as Js, which is enhanced by this factor omega p square by 3 beta upon omega square minus omega p square by 3 beta to the power 2 into the laser field. This is the great advantage. So, though all molecules, all particles may not be having same value of beta, so resonance will not be seen by everyone, but even if 1% particles see, or a few percent particles see this resonance, then the field enhancement is very, very large. That is the great thing. So, this is the basis of surface enhanced Raman scattering. If you really look into the literature, that now we understand this physics with great simplicity and with clarity, but in 70s when this was demonstrated for the first time, people developed all sorts of very fancy and very lengthy calculations, but I think now we understand it very simply in terms of the plasmon resonance. This is the plasmon resonance. I think now I would like to tell you something about the nanotubes. I think before I go to nanotubes, I should mention something about the Rayleigh scattering. Our colleague has developed a theory for Rayleigh scattering. We have done this calculation, but let me tell you what is the physics. Rayleigh scattering has been known to be responsible for the blue color of the sky or red color of the sky during sunset, sunshine. What has been happening is like this. If you take a gas here, bring in electromagnetic radiation, then the gas is made of many atoms. It is made of molecules, but forget the molecular characters, just look at an atom. Electrons are rotating around the nucleus in each atom. So, when the electrons or electron cloud of an atom sees the electromagnetic wave, these electrons experience a oscillatory electric field of the laser, of the light, and they start oscillating. So, each atom becomes a oscillatory dipole. So, the electron cloud is essentially undergoing oscillation like this, and this becomes like a small dipole, it radiates. And dipole radiation, if I calculate the vector potential of a dipole radiator, it turns out to be current in the dipole into length of the dipole into mu 0 times this quantity upon 4 pi distance r. Suppose I am finding this oscillatory dipole with equivalent current I of length dl, then at the distance r, the vector potential due to this would be this quantity exponential minus I omega by t minus omega by c into r. This is the expression for vector potential at a distance r due to a small dipole. Now, what is current? if the electron is oscillating, then IDL is proportional to the oscillatory velocity. So, this quantity is proportional to oscillatory velocity of the electron cloud, and magnetic field that is produced by this radiation field, which is equal to curl of A, and the curl I can replace by at a far distance by I omega by C, like equivalent k vector, and this is the radial direction cross A. An important thing that I wanted to make was that B is proportional to the magnetic field is proportional to omega. Higher the frequency of the laser that is impinged, higher the magnetic field of the scattered light, and this will be proportional to V oscillatory also. If oscillatory velocity is proportional to velocity also, omega also, then this will be omega square dependence, and the scattered power goes as the square of magnetic field, and hence you will get omega 4 dependence, which is the conventional Rayleigh scattering. Now, what happens in the case of clusters? When the laser light is impinged on a cluster, you are having a cluster, big cluster, which has many electrons. Suppose I am sending my light from here. This is the electric field of the laser that is impinged on the cluster particle. Size of the cluster is much less than the radius of the electromagnetic wave of the laser wave. Now, the electrons, every electron is oscillating here like this, and this every electron that oscillates here has an excursion that goes as EE laser upon m omega square minus omega L square omega p square by 3. So, there is an enhancement in this quantity, and how about the velocity of oscillation of this electron cloud, which is equal to d delta by delta t, a rate of change of displacement, delta is the displacement. So, this is equal to I omega into delta. If omega is much less than omega p square by 3, then obviously delta will be independent of omega p and V will be proportional to omega. However, a very important thing occurs when omega is close to omega p by root 3, that this V is enhanced by this resonance, and hence the Rayleigh scattered signal is enhanced by this resonance. That goes as B field, that goes as omega times V, this velocity, this scales as omega divided by, or omega square divided by omega square minus omega p square by 3, and that is a big advantage. So, people have seen in simulation and in experiments also orders of magnitude enhancement in Rayleigh scattering when omega is close to omega p by 3, p square by 3. One thing must note that many, even if this resonance is not satisfied, what Manoj has seen that if you have a high intensity laser, the cluster expands. When cluster expands, omega p decreases. When omega p decreases, even if initially omega was too small as compared to omega p square by 3, but as cluster expands, a situation will arise when omega will become comparable to omega p square by 3. At that instant, sudden enhancement in Rayleigh scattering takes place. So, that is the thing that has been observed, and I think it is a very fantastic observation. The phenomena that I discussed today have been essentially limited to laser coupling with clusters. A very similar phenomenon takes place when you are dealing with carbon nanotubes. Carbon nanotubes are essentially cylinders of length of the order of a few micron, but size typically of the order of 10-20 nanometer. So, the physics is very similar. If you shine laser light, and TIFR group is doing a lot of experiments on this, you will see the same kind of thing, enhancement in ion energy, enhancement in absorption, and also they have observed strong enhancement in X-ray emission. I think if time permits, I will discuss some of these effects tomorrow. But I think this plasma physics at nano dimension is getting very attractive, very exciting these days, and I think it will have a lot of device applications also. And here we are dealing, today I talked to you about plasma balls, but even if the plasma is not created, there are already small metal balls. Like in the case of SERS, surface enhanced urban scattering, I told you that carbon nanoparticles behave like plasma balls because there are free electrons in them. So this physics is getting very exciting these days, and I think we shall continue our discussion on that. Thank you very much.